All right, today we're going to look at Riemann sums. You may look at that and go, that's a really weird way to pronounce that. It's because it's not English, it's German. In German, when you have two vowels together, it's the second one that has the long vowel sign, as opposed to in English, it's the first one. Language is weird. And when you have a double N at the end of a word in German, it makes the vowel before it long. It's Riemann, not Riemann. Or I actually heard someone doing a presentation once where they called it Riemann sums, and I was like, oh gosh, that offends every German ever born. Anyway, so what we're going to do is use this to estimate the amount of change of something from a rate of change. So for example, if an object has a constant velocity of 16 feet per second, what is its change in position? By the way, what's the other word for, single word for change in position? Think physics, friends. Nope. Change in position is not velocity. Thank you. Displacement. Yeah, displacement, same thing. It used to be in calculus, they didn't use the word, and at some point someone went, you guys are being dumb. There's a perfectly good word for that. It's called displacement. Okay, it wasn't in the curriculum listed anywhere specifically, which was just kind of weird. From time t is equal to 0 to t is equal to 6 seconds. All right, so if it's going 15 feet per second, from time t is equal to 0 to t is equal to 6, what is the change in position? Oh, don't everyone jump at once. No. Why would it be 1 over 16? You said 1 over 16.
I said 16 times 6.
Oh, I thought you said, did you say would it be?
Would it be 16 times 6?
Yeah, my mad hearing skills translated that as would it be? No, it translated that as 1 over 16 times 6. And I was like, what the heck? Yeah, 16, sorry about that, times 6, it's going to go 96 feet. And if you think about the units, feet per second times seconds, the seconds will cancel and you'll be left with feet. This will be the displacement. All right. Now, in most cases, the rate of change, the velocity, is not constant. Okay? One way to estimate the change is then to divide the time into subintervals and assume a constant rate on each subinterval. Now, is that going to give you the exact amount? No. It's just a way to estimate it. So, if we have this table that has, for every second, it has the velocity of an object in feet per second, what we can do is divide this up into little subdivisions and go, okay, and what we'll do is for the first second, if we're doing a left approximation, we're going to take the left value of the velocity, 0, and assume that it's going 0 feet per second for that whole second. So it would be 0 times 1. Plus, the next interval, we're going to use the left-hand velocity, 8, for that 1 second. And we'll do that for each interval. So we'll use 15 feet per second for the next second, plus 21 feet per second for the next second, plus 26 feet per second for the next second, plus 30 feet per second for the last second. Now, at this point, you may be going, okay, why are you multiplying all of them by 1? Well, the time interval is 1 second. And also, almost every example we'll have after this one, the time intervals won't be equal width. So you have to find the width of each subinterval. All right, so this is going to be 23, 44, 70, I think it's 100. Someone can check my accuracy. I've already done this interval. For this interval of 1 second, I'm using the left hand, and we're assuming that that's always what's going to be the velocity. Now, when we do a right approximation, for this first subinterval, what velocity are we going to use? 8. So it'd be 8 times 1. And on the next subinterval, we'll use 15 for the velocity the whole time. Then 21 for the whole time. 26 for the whole time. 30 for the whole time. And 33 for the whole time, which comes out to be 133 feet. The reason I know that is because this first one was 0 and everything else is the same, and I added on 33. Now, we can also do a midpoint approximation. To do that, what we'll do is make a wider interval here and use the midpoint velocity. So, for my first interval, I will use 8 as the velocity for the whole 2 seconds, which is the width of that time interval. Plus, on the next 2-second time interval, I'll use 21 the whole time. And on the last one, we'll use 30 for that whole 2 seconds. So let's see, 29, 59, 108? 118. And each of these is simply an estimate. And we'll talk a little bit later on how we know whether each of these is an overestimate or an underestimate. There he is. It depends on, I was just waiting. It depends on the qualities of the velocity. On this one, it looks like the velocity is increasing the whole time. By the way, do we know that the velocity is increasing the whole time? No. It could be doing all kinds of crazy things in those intervals. We just have some points. All right, page 2. So let's talk about Riemann sums more generally. So consider a function y equals f of x from x equals a to x equals b. A Riemann sum is found by partitioning, that means divided up, the interval from a to b into subintervals. Then selecting an x value in each subinterval, evaluating the function at each selected x value, and then multiplying each function value by the width of the subinterval. Sounds horrible. It's really not all that bad. Let's do it for this one. So, first thing I'm going to do is I'm going to divide this up into subintervals. So here's my beginning point, my starting point. Everyone's doing this on their paper. Yes, we are. With a Riemann sum, unless you're directed to, the widths don't have to be the same. So I'm going to put a partition here. And I'm going to make this one kind of small. And I'll leave that one really insanely large. Okay, so I have partitioned this into 3 subintervals. And then, again, unless you're directed to use the left side or the right side or the midpoint, you can pick any point you want inside of it. So I'm going to pick this point and call this one x1. And let's go over here and I'll call this one x2. And it doesn't matter where it is, I'm going to call this one x3. Then what we're going to do is find the y value. F of x1. And then the y value here, f of x2. And the one over here, f of x3. There seem to be a lot of people just wandering around today.
This is Miss Gentry's class.
Ah. Okay. So then what we'll do is we'll take that and multiply it by the width of this subdivision. Well, when you multiply it by the width of that subdivision, what you're actually doing is finding the area that's enclosed here. Because you're taking the height times the width. And then we'll do the same thing here. That one's almost the same height. And then the one over here, I add those 3 areas together, that's a Riemann sum. And this is the most general form of a Riemann sum you can have. Divide it into some subintervals, find the height at some random point, multiply it times the width. Yes, sir?
So it's from a to x1 times the height
No,
plus.
no, it's all of this times the height. It's the width of the subinterval. And then we're going to take the width of this subinterval, so like this, and then the width of this subinterval, right, all the way to where I partitioned it. So the distance between the partitions. All right? So a Riemann sum is equal to the summation as I goes from 1 to n of f of x sub I, that's the height, and delta x sub I, that's the width. N is the number of subintervals. X sub I is the ith x value, so I picked 1 and 2 and 3. And delta x sub I is the width of the ith subinterval. So the width of each of those. Now, if f of x is the rate of change in a function, f of x, the Riemann sum estimates the change in f of x from x equals a to x equals b. That is, capital F of b minus capital F of a. So if little f of x is the rate of change of capital F of x, then the Riemann sum gives you an estimate of the change. Just like we did a moment ago, we had velocity. That's the rate of change in the position. Right? Since it's the rate of change in the position, the Riemann sum estimated the change in position. All right? Now, if a function is strictly increasing, a left Riemann sum is going to be less than the true value, and a right is greater than. Because if we go back to this, if this if the velocity is always increasing, well, when I use a right Riemann sum, I'm always using too much velocity. And if I use a left, I'm always using too little. On the other hand, and I always have to think about this one, if a function is concave up, so let's say we've got this function that's concave up. And we use a midpoint Riemann sum. So we would be using the midpoint as the height of my rectangle. Do you see how I have a whole bunch here that I'm not catching? And I have this little piece here that I'm catching that I shouldn't, and this even smaller piece here that I didn't catch. But these two pieces that I missed is bigger than the part that I overestimated, right? So if a function is concave up, the midpoint Riemann sum is less than the true value. And conversely then, if it's concave down, the midpoint Riemann sum is greater than the true value. All right, well, let's look at a problem. We're going to be looking at number 5. You will see this problem again. I don't remember where, maybe on tonight's homework. I don't even remember. But I seem to remember it shows up again and someone's like, isn't that the one we did in class? And I'm like, yes, did you get it right this time? So let's take a look. This is right off of an AP exam. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. For the time interval from 0 to 12, the graph of r is concave down. The table above gives selected values of the rate of change, r prime of t, of the radius of the balloon over the time interval from 0 to 12. The radius of the balloon is 30 feet when t is 5. And then it very nicely gives you the equation for the volume of a sphere. Okay. So let's take a look. Let me see how we're doing on time just to make sure. 11:26, this class is over at 35. We should be all right. Not all of this is talking about Riemann sums, just part of it is. So it says, estimate the radius of the balloon when t is equal to 5.4 using the tangent line approximation at t is equal to 5. All right, when you get to a period on these, do that if it has a direction, right? Read the rest, but don't try and do them both at once. Is your estimate greater than or less than the true value? Give a reason for your answer. All right. I'm going to work up here where I've got a little bit more room. You can work wherever you've got space. And I know there's not tons, but all right. So to write the tangent line approximation, I'm going to do y is equal to, and we're trying to estimate the radius. Well, the radius of the balloon is 30 when t is equal to 5. That means it's going through the point 530. So I've got a point. And what's the rate of change? Well, that's our slope. That's 2. So I can write the equation. This will be y is equal to 30 plus 2 times x minus 5. So then the radius is approximately equal to, at t is equal to 5.4, that'll be 30 plus 2 times 5.4 minus 5. By the way, you do not have to actually calculate that. This is a free response question. They do try to make it easy for you if you do, though. because 5.4 minus 5 is 0.4 times 2 is 0.2, so this is, times 2 is 0.8, that's 30.8 feet. Then they ask the question, is your estimate greater than or less than the true value? And the reason is buried almost right in the middle of this. It's because the graph of R is concave down. Because if we look at the graph of R and it's concave down, and we do a tangent line approximation anywhere, and then we estimate, is our estimate going to be too big or too small? It's going to be too big. So it is greater than the true value because the graph of R is concave down. All right, let me get rid of all that so I have some more room. Find the rate of change in the volume of the balloon with respect to time. The change in volume with respect to time, that's a related rates problem. You should immediately cop to that as soon as it says the rate of change of something with respect to time. So what do we want to know? Well, we want to know what is dV dt. And we know that the volume is 4/3 pi r cubed. So dV dt, when I multiply the 4/3 times the 3 is 4 pi r squared. And since I'm taking the derivative with respect to time, and this variable is not time, we have to apply the chain rule. That's times dr dt. All right, so we know that the time is 5. Oh, at time 5, r is 30. And dr dt is 2. Right here in the table. Indicate units of measure. Okay. So that's got to be cubic feet per minute because it's change in volume with respect to time. All right, then part C, finally, ask about a Riemann sum. Use a right Riemann sum with the 5 subintervals indicated by the table to approximate, I don't know what that is. Actually, I do. But it doesn't matter that you don't know what that is. It told you to use a right Riemann sum. So even if you don't recognize that, and you will shortly, you can still do the right Riemann sum. So with the 5 subintervals, our right Riemann sum tells us that whatever the heck this thing is approximately equal to, so I'm using subintervals as given in the table, and I'm using the right side every time. So for this first one, I'll use 4 feet per minute for the first 2 seconds, plus 2 feet per minute for the next 3 seconds, plus 1.2 feet per second for the next 4 seconds. Hang on a second, did I lose it? 2, 3, I'm sorry, 1.2 for the next 2 seconds. Then 0.6 for the next 4 seconds. And then 0.5 for the last second. Again, this is a free response question. There is zero need for you to calculate what this value is. Okay, you should put units on it though. And here we're multiplying feet per minute times minutes, so that's got to be feet. And we just learned a moment ago that if we do the Riemann sum of a rate of change, it's going to give us the change in whatever that's the rate of change of. Yes, that's a horribly twisted sentence, but I think you got it. This is the change in the radius.
And that's the change in the radius over the interval 0, 12. 0,
Yeah, from t is equal to 0 to t is equal to 12 seconds. All right, y'all have a great rest of your day, and I'll see you hopefully at,
Should I copy that?
oh, yeah.